Hi, this is Sieg Schmalz, Applications Engineer at Microchip Technology. Welcome back to the PCIe QuickLearn video series, where we focus on providing you PCIe overview information with a primary focus on the timing aspects of PCIe. In the previous video, we learned some of the basic PCIe terminology, as well as some general features of the PCIe bus. In this video, we'll focus on what is by far the most popular clock architecture for PCIe implementations. All PCIe devices are driven by a clock, and this clock needs to adhere to certain performance specifications. The Common Reference Clock architecture, also known as the Common Clock architecture, is the most widely implemented method for clock distribution among PCIe devices. So we are going to focus on this one. And now, please welcome the returning stars of our video series, Device A and Device B. Next, let's have them driven by the same clock reference. We see that what they have in common is this reference clock. Let's add in the data link, and now we have a simple representation of the common clock architecture. You may recall from the previous video in this series that a data link is actually the combination of one or more lanes, and that each of these lanes, in turn, consists of two one-way data paths between device A and device B. We are going to focus on one of these paths. In a perfect and ideal world, the clock driving the receive latch is an exact duplicate in frequency and phase of the clock driving the transmit latch. In real applications, of course, the reference clock is altered as it progresses to the transmit and receive latches. Any jitter present on the reference clock is low-pass filtered by the transmit and receive PLLs, and the clock and data recovery block high-pass filters its incoming clock. These filtering effects are modeled by the PCIe standard as transfer functions in the Laplace domain. Now, we should note that the transfer functions are different for each of the various blocks. Furthermore, as the PCI specification has evolved over the years, the way it expresses these transfer functions has progressed and changed as well. Therefore, each different PCIe version expresses these individual transfer functions, well, differently. While I know that you would like me to go through the math derivation of how the clock jitter transfer function shown in this formula is derived, I am going to do what we see in many engineering textbooks and say, it can be shown that, or maybe I should have said the derivation is left as an exercise for the reader. Not only are the individual transfer functions for the transmit PLL, the receive PLL, and the clock and data recovery block different for different PCIe versions, there are even multiple choices for each transfer function within each specific PCIe version. When we figure out all of the possible ways that the individual transfer functions in a specific PCIe version can be combined, we see that there are many possible calculated jitter transfer functions that apply to that specific PCIe version. In other words, each PCIe version contains many models to describe the jitter of the clock on the receiver latch relative to the clock on the transmit latch. As PCIe lane speeds have increased with each successive PCIe version, the magnitude of the allowed RMS jitter has had to decrease in order to maintain acceptable bit error rates. Remember that the jitter transfer function, h jitter of s, for a specific PCIe version is applied to the reference clock to calculate the PCIe post-filtered jitter, which we show in this table. This is really important. The worse the post-filtered jitter on your reference clock, the more bit errors there are when device A communicates with device B. Now, the more bit errors there are, the worse the data communication link is. And when a communication link begins to have errors, well, you know what happens. It is not good. But no need to worry. You can avoid this terrible fate by using devices that have been specially designed for PCIe applications, such as the multi-output ZL30282. Well, that wraps up this video. I hope you enjoyed it. And if you'd like more information, feel free to visit our website at this link.